Okay, with the introduction of atom done, we will now get to look at how electron cloud is actually being organized in an atom. Before we do that, we're going to start off with something that you understand back in O-level, where you actually represent, say, for example, sodium in this manner, draw a circle around it, and you say that's the first electron shell, and you put 2 electrons. And thereafter, you go into the second electron shell, and you put them in pairs. Okay? And obviously, as you move further up, you could actually have more space to actually accommodate more electrons. And based on this concept itself, you will find that at the A level, we will expand it by discussing how electron shell can be organized into subshell, and from subshell into orbitals. All right. So be familiar that we start off by looking at electron shell. From shell, you can organize into various subshell, which is various space, dedicated space for the electron to sit in, and each space typically can hold up to 2 electrons, all right? And the electrons are in pairs because although they have like charges, they are oppositely charged. So magnetically, they attract each other, although electrostatically, they repel. So that is how the space in an atom is actually being organized. So let us start off by looking at the first electron shell. Let me represent this dot as the nucleus, all right? So in the immediate space around it, you need to house 2 electrons because we know the first electron shells can house 2 electrons. So when the electron shell can house, first electron shell can house a maximum of 2 electrons, it makes sense for it to use the immediate spherical region for it to put the 2 electrons inside, all right? So what we term this spherical space, we call it the S subshell, all right? So this is actually termed as 1s subshell because it occurs in the first electron shell and it only has 1 orbital. And because it has 1 orbital, the total number of electrons that it can hold will be 2. Okay. If you now take a look at the next phase, you will find that immediate to it, you can actually put another 1 more spherical region around it, all right? And we can put another 2 more electrons. So in the second electron shell, you realize that it will have actually a subshell called 2s, which is further out. Certainly, there's still empty space here. We could organize the space into a 3-dimensional according to the x, y, z, x, y, and z, all right? And based on this orientation, we could actually try and occupy them, all right? Occupy the space. So as you probably could have seen, they are actually now, you actually now get a different shape, all right? For the, in terms of the subshell. And actually how we label them is that we say that all these subshells is a different shape. So therefore, they actually come in the dumbbell shape, all right? As you can, as is displayed here. More importantly, you realize that for this 2p subshell, there's actually 3 orbitals because there's plenty of space that they can fill it up. And therefore, because of this, we need to bear in mind that there's in total, for 2s, there's one orbital, 2p has 3 orbitals, so total, there are actually 4 orbitals. Because there are 4 orbitals, the total number of electrons in each orbital is 2, so hence it is 8. Certainly, we're going to work on the third electron shell, which is actually almost the entire space. And the pattern will kind of repeat. By now, you probably would have seen it. The third electron shell will definitely have a 3s and 3p. And without further drawing, you probably realize that because the space is much bigger, all right, as you draw the dumbbell shape, there are still plenty of spaces, all right? So if you imagine there's actually this is actually your 3s, and then we actually have your 3p, all right, on each of the axes. But in between the p shell itself, p subshell itself, there will still be space within it. So hence, you will find that those space could now also be utilized for the electrons, to accommodate the electrons. And therefore, you will find that in the third electron shell, you will have 3 subshell, actually 3s, 3p, and the 3d, all right? And 3d will have 5 orbitals. And we will show you the shape of each of the orbitals in the next minute. And we can run through how those orbitals are being labeled and how they can be sketched. So now let us take a look at the shape, various shape of the subshell. So first, before we start, I want you to understand that orbital is a region of space in which there's the greatest probability of actually finding the electron. So as far as all the S subshell is concerned, they are all terms to be spherical in shape. All the P subshell are dumbbell in shape. And as far as the D orbitals is concerned, there are primarily 5 of them. Each of them are organized in different ways. You can see the top 3 being more similar because they are organized in 4 regions, but all along either the XY plane or the YZ, or otherwise the in the case the XZ. Finally, for the case of dx square minus y square, you need to take note that the 4 electron region is actually below the axis, all right? And dz square itself concentrate more along the z-axis. I think the important thing that you need to bear in mind is that you need to be able to sketch them, label them, all right? And as well as the more important, to know the similarity and the difference between each of the orbitals. So specifically, a good discussion could be that what is the difference between these dxy versus the orbital space here, dx squared minus y squared. One of the difference is that you can see that the axis, xy, z axis, actually do not cut across the region of the electron density, all right? Whereas for down here, you can see that it's actually running, all right, in the same direction as the electron density. Second of all is obviously this sits obviously on the plane xy. This one is below the plane xy. In terms of similarity, obviously you can see that there are 4 separate regions. Their shapes are exactly identical. And one more factors that you can add on is that each of these orbitals will be able to hold up to a maximum of 2 electrons.